demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin. I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close to my body, and I spin around very rapidly. As soon as I move them out, I slow down again. And I can repeat this as many times as I want until the friction of the turntable stops me.
All right, let me go back. Okay, so I usually do this demonstration in P132. So we have a turntable that we put on the floor, and then I have a student, usually somebody that has a really good balance, and I put the student on the turntable, and then we have dumbbells, so the student holds the dumbbells out like that, and then I spin the student, and then all of a sudden I tell the student to go like this, and all of a sudden students start going really, really, really fast. And it's really cool. All right, and so the student's going really, really fast, and then just like we saw in the video, then I tell the student to go like this, and then the student slows down. Now, what's going on? I mean, there's no power source to make the student go faster. I mean, what is going on here, right? Okay, well, we saw that this equation, L equals I omega, we can use that for rigid body, symmetric rigid body, rotating about a rotation axis. Well, we're going to consider the disk. Well, the disk is certainly a rigid symmetrical body, but we're also going to consider the person a symmetrical rigid object. Okay? And so initially, the arms are way out there. So L equals I omega, which is constant. Because we're going to say that there's very little friction in the turntable. So, all right. So no external torques. Okay, so we have I omega initial equals I omega final. Now look, if the guy is holding the dumbbells really, really far away from the rotation axis, that means that remember I, right? That means I is really, really large. Okay? So initially, I is really, really large, and omega is kind of whatever, small. All right? But then, when the person goes like this, then this R gets smaller, so I all of a sudden gets smaller. But again, this has to equal that, so the omega has to increase, right? So initially, large I, average omega, then small I, so the omega has to increase. There it is. It's no magic. It's just conservation of angular momentum. You've seen at the Olympics, the figure skaters, at the end of their routines, what do they usually do? They start spinning, right? And then all of a sudden they pull in their arms, and then they start spinning really, really, really fast. So that's the principle. That's the principle. Okay, this is just kind of a summary. Angular momentum is a measure of the strength of an object's rotation about an axis. Newton's second law, in rotational motion, the sum of the torques equals delta L over delta T. This means that an object will maintain its angular momentum unless acted upon by an external torque. Okay, now you're going to learn something useful, believe it or not. We all know that it is easier to balance on a bicycle that is moving than on a bicycle at rest. If you don't believe that, try it. Rotating wheels have angular momentum. To tip the wheels means a change in angular momentum, the direction if nothing else, right? Which requires a greater torque than tipping the wheels at rest. All right, that's important. So, one of these days if you have a child and you're teaching your child how to ride a bike, where should you do it? You should do it on a slight hill, a slight downward incline, hopefully grass, because then the bicycle will have some, it will be moving. And so it has angular momentum. So it's much more difficult to tip a bicycle that has angular momentum, that has a lot of angular momentum, than it is to turn a bicycle or tip a bicycle that has a small amount of angular momentum. So there you go. Learn something new. All right. Now we're going to do it. Angular momentum. It even has, it's important in astronomy. Okay. So how do you form a star? So a star forms as a gigantic gas cloud. So here's a gigantic gas cloud. Now, what's a gas cloud? It's made out of mostly hydrogen, a little bit of helium. Well, they have mass, right? So they have gravitational attractive forces. So let's say you have this gigantic gas cloud. And let's just say it has slight rotation, which is not all that unusual. So here you have this giant gas cloud. It has a super small rotation. But, all of these gas particles are attracting one another, right? So the gas cloud is collapsing. Well, what does that mean? Here, it has a large rotational inertia because it's all spread over, or it's far, has a large R. But as it collapses due to gravity, the R decreases. So the I decreases. So what has to happen to the omega? It has to increase. So the gas cloud in deep outer space spins more rapidly as it collapses because of the conservation of angular momentum. And you see that, all right? You see that in the universe. So once again, good old angular momentum. Okay, here's a challenging homework problem. So what do you say we do it? So everybody read it, please. All right. So 2 children, mass M, riding on a disc-shaped playground merry-go-round. Mass 2M, initially standing on opposite sides as it rotates with an angular speed omega. Then the children move towards the center until they're at this location. And how is the angular velocity going to increase? Now, and then we'll do that too. Now, here's kind of a hint. You notice on this problem, the kids first are here, and then they move here. So there's a before and an after. And we've seen this before, right? Whenever there's a before and an after, it's usually an indication there's a conservation law, something is conserved. So as soon as you see that before and after, you should be thinking in your head, conservation, something is conserved. And then, this thing is going around in a circle, so you should think, conservation of angular momentum. I mean, hopefully that's what you should think. Okay? All right, now, hold it though. In order to use conservation of angular momentum, we have to make an assumption. So what are we going to assume about this merry-go-round? We have to assume that it's frictionless. So that just means it's really greased well. All right? And what are we going to assume about the children? And we don't know what the angular momentum is of a child. So we're just going to assume that the children act like point particles. Right? So we're just going to use this for I. Because what else can we do? I mean, that's all you can really do. All right. So here we go. All right. So the rotational inertial for a particle. So for particle is particle. Okay, for a particle, that's I. For a disk, you have to look this up. You don't have to memorize it. For a disk, the rotational inertia is 1/2 mr squared. And that's in that table I showed you earlier. Okay, so question number 1. We're saying that angular momentum is conserved. So L initial equals L final. So that means I omega initial equals I omega final. All right, what is I omega initial? Well, we have the disk, right? We have the disk spinning, and we have the kids spinning. And so we have I disk, and there's two kids, right? So plus 2 I, I'll be polite, child. Okay? So that's initial times omega initial. And then for final, we still have the disk. And we still have the kids. Final, omega final. Okay? There you go. Now, let's do it. So what's I disk? It's 1/2 mr squared. Oh, hold it. 1/2. Now, what's the mass of the disk? It says 2m. 2m. What's the radius of the disk? R. Okay? And then for the children, it's 2 kids. And we're just going to say that their rotational inertia is just the mass times their distance from the rotational axis. So 2 kids, the kids have a mass m, and the distance is r, right? Mr squared. And that's multiplied by omega initial. Okay, that's good. Then for the final, we have the disk again. So 1/2 the mass, the radius squared, whatever, who cares. Then we have 2 kids. But where are the kids now? The kids are no longer at r. They're at r over 2. So this, right? So r over 2 squared. And then omega final. Great! Okay, now we can do some stuff in our head. So this 2 kills that 2, so goodbye. Then we have mr squared plus 2mr squared, that's 3mr squared. So we have 3mr squared omega initial. And then here, this 2 kills that 2. So we have mr squared. Wait a second. Oh, I'm good. Okay. And this is r over 2 squared. So let's be careful there, right? So that's r squared over 4. Yeah. All right. And this 2 kills that 2, so we have that. So this is mr squared plus 1/2 mr squared. That's 3/2 mr squared. Omega final. So therefore, let's go up here, right? So therefore, let's solve for omega final over omega initial. So that means we're going to divide by omega initial. Then we're going to divide by this mess. Okay, and so we have the mr squareds kill, and we have 3 divided by 3/2, which is just 3 over 1 times 2 over 3, which is 2. Okay, so that's 2. Okay, so what are we saying? When the kids move from here to here, the omega increases by a factor of 2. By the way, this is a really good test question. You should make sure you know how to do it. Okay. Okay, now let's do part B. Okay, part B or 2, whatever it is. 2. By what factor does the children's tangential speed increase? So tangential speed, v equals r omega. You better not forget that equation from way back when. Okay, so initially, we're just going to say v equals r omega, right? V equals r omega. So, all right, so here, let's do this. All right. So initially, here they are at r, and they have speed omega. But then afterwards, what's their distance from the center? R over 2. And then what's the omega? We just figured out it's 2 omega, right? It doubles. So the 2's kills. The 2's kill, so we just get R omega back. Okay, so in other words, by what factor does the merry-go-round's rotational speed increase? It doubles. By what factor do the kids' tangential speed increases? Doesn't. It's the same. It's the same. Okay. All right. Woo! So let's review. Okay, so we talked about impulse. That's a big deal, right? Impulse. And impulse is the area under the force versus time graph. It's also the change in momentum. It's also the force times the time. So that's a long theorem, impulse momentum. Then we found the linear momentum, right? Linear momentum is mv. Okay, impulse momentum theory, I already said that. Talked about conservation of linear momentum. Then we learned about angular momentum and conservation of angular momentum. Okay, impulse momentum theorem, there it is. J equals area under the F versus T curve, which is F average delta T, delta P, P minus P initial. Momentum conservation, if it's an isolated system, the momentum doesn't change, it's constant. Angular momentum, we only learned one formula in so far anyway, right? So linear momentum, P equals mv. Symmetrical, rigid body rotating about a center of gravity, L equals I omega. If you know this, this is free. Just like this, here we have the sum of the torques is delta L over delta T. Isolated system, sum of the torques is 0, L equals constant. And that's it. Thank you very much. Okay.